So good morning. And so, second lecture, and promised today we will discuss what's called a logistic growth and logistic equation or model. But before we start with that, let me discuss a little bit more what we have discussed yesterday. So the take-home message was, okay, so our models, mathematical models of populations, describe the population sizes. Okay? Can be measured in individuals or even weight or something. Okay, the population size. And we relate change in time of the population, because the population can be changing, to biological phenomena that induce this kind of change. And we translate this mathematically. Okay? So that's the general framework. And the first model was simply saying that that the per capita change in time is due to a constant rate of birth minus a constant rate of death. So that was the thing. Okay, so this has taken us to one equation, which was the Malthus equation, which is an equation that we can solve, and the solution is an exponential in time. Okay, if birth rate is bigger than death rate, then this is an increasing exponential in time, whilst if death rate is bigger than birth rate, then it's an exponential that decreases in time. And then we came to the important discussion about the validity of this kind of thing. Because, well, as you saw, exponential growth is something which is really, really gigantic. It's something very quick, and we obviously don't see this in general in nature. Okay. Well, then what I want to still discuss today is, so first of all, okay, we had this equation. Okay. And the solution was the function n of t, okay, which is the initial population exponential of r times t. Okay. So in principle, this equation says that if I know the population at time 0, which is an arbitrary time, it's the time I start to measure. Okay. Then I know the population size for any other time precisely. So this is in contrast with what Paulo told you yesterday, okay? Now obviously, there are fluctuations and so on, and when you measure things, it's not like so much precision, okay? So this is called here. So this is to introduce some jargon, because sometimes it's important to know the jargon. Like people speak with jargon, it's better you know what they mean. So they mean that the jargon here is that this is a deterministic model. So deterministic model are made pretty much as inspired by physics, or where you have a lot of deterministic models. For instance, the Newton law, right? And so deterministic models are always only an approximation. Okay, so in a world of population. So let's compare things with physics and ecology, or population biology in general. Okay? In physics, you can manipulate in the lab so many things that you can actually go and look if your solution to a problem which is described by something which is deterministic, if it is actually obeying what the result of your model is. There's always a finite precision, but sometimes there's a precision, but super high precision. So we don't go into the problem of the theory of knowledge here, because obviously all knowledge, all measurements are finite, okay? So, and you don't have anything like infinite time. So these are abstractions. But in physics, you can manipulate the things to such a point that you pretty much get convinced that your theory or your model holds. Now, what's the secret? The secret is isolate your systems in such a way that actually what you are studying, say, problem in electromagnetism or mechanics or whatever, that you suppose, the theory is supposed to, let us say that in vacuum happens this and that. And then you are able to produce vacuums. And therefore, the hypotheses are, if not completely fulfilled, they are very close to. Now, come to biology in general, but it's a little bit different when you have, molecular biology, then have labs and but population biology connected to ecology is completely different, because you don't have a way, usually, to manipulate your system and isolate and produce conditions that are very close to the hypothesis you made about the model. Why? Why? Because there are so many connections between species and environment. Say you have a focal species, you are studying a certain species, but this interacts widely with many things, and then behavioral things. I didn't mention this, but here the number n, it's a continuous number, okay? It's a continuous function. It can be any real number, okay? But we are counting individuals, which are integers. So this is only a good approximation if the number n is large enough, okay? Because the variation from 10,000 to 10,001 is more or less almost like, it's well described by a continuous function, okay? So that's the first thing, okay? So, but it's in practice, there's no such thing as individuals being a real number, okay? So this is an approximation, this is a way to study the thing. So there are so many things that you cannot actually manipulate in the lab, except for cases like E. coli I mentioned yesterday, because E. coli is simple, and you can grow it on a Petri dish, and then you are okay. But it's very restrictive if you want the population biology to work. It works only for some species. Okay, so we cannot, in general, have the same procedure as the physicist or even the chemist. So, and then you can ask yourself, okay, well, so what's the status of a law like Malthus law, okay? So, in order to give a glimpse of what could be, there are laws that are limiting laws that are not necessarily verified, but that you hold to them. So, consider Galileo Galilei at Pisa Tower, okay? Saying that if it throws two bodies and they will fall at the same speed and the same time to reach the bottom, okay? So actually he never did this, okay? It was not an experiment, it's a mental experiment. And if you do it with precision, it's not true, okay? Because the time, there's air, and obviously he was not thinking about there's air. So, okay, and air interacts with the bodies. If the shape of the body is a little bit more complicated, maybe the friction with the air will make a small difference. Probably a second or not very much. But it's not completely true. So what he is meaning is if I had no air, which is something that at his time there was no such thing, they would fall at the same speed and take the same time to reach the bottom. So this, you could also say something similar with Malthus law. Malthus' law says if there is nothing that objects the growth, then it will grow exponentially. So this is the point. It will grow not in any form. It will grow exponentially. Yeah. Yeah, there's, where's the mic? Okay.
You were saying that a deterministic model is when you have the values on the right side, you can have the precise value on the left side.
Yeah, sure.
There are different types of model.
Yeah.
What is a non-deterministic model?
Non-deterministic model is a stochastic model. A stochastic model, you don't speak about the value of n, of the number of individuals, but the probability that the number of individuals is a certain number. Okay? So that's pretty much what Paulo showed you. Okay? So you can have models that have a completely different base. It could be like this. Instead, you can simulate birth and death rates processes. You say I have an individual here, and there's a probability that he will give birth to a new generation, and there's a probability that he will die. So they do this for all the individuals. Okay? So this is a stochastic model. Okay? This stochastic model can actually, when the number of individuals is very large, then you have procedures, which is stochastic dynamics and statistical mechanics and physics, to scale up from this individual description, which is probabilistic, to a higher order, which will be something either deterministic, where n would be the average number of individuals, or a stochastic differential equation. This is a differential equation which has noise. Okay, this is something Paulo maybe mentioned and so on. So this is, would be, and then there are other things. So you can also have models which are, for instance, agent-based models or individual-based models. For instance, that's something that people do a lot when they want to study something which is called spatial ecology. Spatial ecology means I will take into account the spatial dimension of my population. Okay? We are not taking here. We are implicitly saying we have a certain region and we studied population in that region. Okay? But we have never asked the question, well, in this region, are they all together in a corner, or are they homogeneously distributed? So we didn't, and that's not a part of our course. But this is, spatial ecology is an important part of ecology. And for instance, then you can say, I have individuals and I have rules for the individuals. I don't have any equation. Okay? I have rules. Say, if the individual, he will give a random step in a certain direction. But if he comes close to the other guy, then maybe this random stack has a bigger probability to go opposite, or maybe they become friends or something. You can simulate all of this, and these are not deterministic models. Right? The deterministic models have this kind of illusion, but which I'm trying to convince you that you should accept, that everything is determined from now to until the end of time. Okay? So again, so you have the deterministic models, and here you have clearly a problem with this model because it grows forever. But in an analogy to the Galileo case, okay, you can think that this would be the case if nothing opposes the growth. Okay? And the important statement is not only that it will grow, it gives you an expression, it's an exponential. Right? So this is the main message of Malthus, and which means that now when you go in the field, you see things don't grow exponentially. Okay, yeah.
It's just to make a comment about the question he made. I would just like to say that the deterministic models take into account the initial conditions of the parameters of the model, and the statistical models use the probability distribution to estimate the parameters. Just a comment.
Yeah, exactly. So we here, in order to make any, say, so predictions, I need the parameter, which is the initial condition. Okay, this will always happen in the other equations also. I need initial conditions. I need to know the state of my system, of my population now, in order to say what will happen with it. If I don't know even what's now in the number of, I cannot predict anything. Okay, and so again, but the fact that we expect exponential growth, if nothing opposes the growth, this means that when we do not see the exponential growth, we have to explain it. Okay? Then you say, okay, we expect exponential growth, but we see a constant population. Or an oscillating population. The population goes up and down in time. So then you have to explain this, okay? Because you would say that the basic law would be in Malthus, but it's not been observed in Malthus because some hypothesis of Malthus' law, which is the constant rates of birth and death, is probably not true. And then you have to modify in such a way to incorporate new biological mechanisms that will give you a better approximation of what happens. Okay, so this is the idea about the Malthusian law, and this will go. This will go with us. This kind of thinking that you get a framework to think about the ecological problem. So this is very important because you could also think about, I want to study populations, and I go and I measure things, and I'm a completely empiricist. Okay? I could do something very empirical, okay? Without writing models or without having theories. In ecology, not every theory is mathematical. There are theories or models in ecology which are only conceptual. They are not mathematical. But anyhow, it's still, if you do it with rigor, you have a framework which it's precise. And then what you want in ecology is usually, let's say, in order to think about your systems, so maybe you have a community of several species, then if you only do descriptions and correlations, say, between population sizes and external things like temperature or rainfall, okay? And then you say population size, you could just measure this and put it on a machine learning algorithm that probably can predict something for you, okay? So this is first criticism that you will hear about machine learning. Everyone knows what's machine learning here, probably it's sameness, okay? At least in the newspapers. And so you could do this, and you could have some nice results, also predictions maybe. Because if you have a lot of data, your machine learning algorithm, which is pure statistical stuff, which works with correlations and so on, would maybe give you something good. But then you don't understand why, actually. Why is this happening? In order to understand why, what are the mechanisms? Why is that the increase of temperature makes the biodiversity decrease? So you can observe, and you can do this kind of super data-based thing, but you don't know mechanisms. And in order to talk about mechanisms, you need a theory. And the theory, and here we will do it in mathematical terms, the theories, okay? But even if it's not mathematical, you need a theory. And then once you have a theory, it is natural that certain questions arise. As now, if I have the theory, say exponential growth is what you expect in nature, and when you go there and you don't see the exponential growth, then you have a reason to ask why not exponential. If I didn't have this theory, the question why is there no exponential growth would be completely nonsense, because why would there be actually So I have a theory that says it should be, and we can obviously come to the conclusion it's completely wrong theory, but it's not the case here. Then the question, why not exponential, makes sense. While if I don't have a theory, I don't have a framework to think about things, I would say, well, you could ask the question, why not a population is grown like a polynomial, second order polynomial? Well, it's also growing and so on. So that's the reason that this asking why not exponential and not why not quadratic, the reason is this comes from some hypotheses which were put into a mathematical formalism and that give you the exponential and not quadratic curve. Right? So that's the meaning of how you use this kind of theories, the deterministic and even stochastic theories, in systems which we call complex systems. This complex systems in ecology is always something complex systems in the sense that you cannot do what physicists do with the lab. They have many interactions and many of unknown interactions. Okay? That you don't even know exactly which species are interacting and what's the effect of environmental variables on the species fecundity or death rate or whatever. So, okay, so this is what I wanted to say about what we had discussed yesterday about determinism and about the status of theory when we talk about complex systems, in particular in population ecology and in ecology in general. Okay? So let's go to the next topic. Any comments about this? You can ask or just comment if you want. While I drink a little bit of water. Okay, first, then you. It's okay.
Okay.
Yeah, you have to speak exactly in the position of this.
I do have a question. I'm not sure if it's actually like the best time to ask this question, but so we're talking about modeling with data, and usually what I know how to do or what I have done is you have a lot of data from the past, you do a model, and you see if your model is actually accurate with what you know that happened in the past. And that's a way to validate your model. But when we talk about predicting or prediction models in biology or ecology, that you don't have any past data, that you want to try to predict something, how do you validate your model? You know, not having anything from the past.
So there's a problem with data. These are what we call dynamical models, okay? It's about the variation in time, okay? So these models, as I told you, like Malthus, it's not something that you can validate, but you can have something like it's valid on a certain time scale. But you have to have measurements over time, okay? You have to have measurements over time. In this case, this particular case, where we are modeling the time change of things, okay? Yeah, and most of the time you would, if you have more precise models and so on, you would validate them with data from the past. You need data from the past. You have measurements over time.
Do we have any way to validate our models if we don't have any data from the past and we're trying to predict something? I think that's my question, actually.
Yeah. Really predict not. You need some data. Okay, but we will see in the next classes will become more clear that we are not so much in the business of predicting. We are trying to explain. For instance, we will see that competition between species, which I will explain what it is, leads always to the extinction of a species in favor of another species. And this is something very basic of natural selection. Okay? And then you can see, sometimes you can go and see that there is actually this phenomenon, which is called competitive exclusion, competitive exclusion. So you can see this in the lab with what Paulo showed you, this book from Gause. The second part is about competition, actually. And so you will sometimes predict the pattern of coexistence or of dynamical behavior, say cycles. And these things are not so precise, but they are important, and they come from the models.
Morning. I was thinking how do we test the reliability of our model to see if his works?
These models. So one thing you can think is remember Paulo's class, okay? So you need data. Paulo was talking about an increase and then a saturation of the rate of increase and so on. And, well, you showed it. I showed data. Then, okay, your data are not exactly have finite precision. You have duplicates, and you do the statistics, and so on. And then you see that the model is predictions are consistent with the data. Okay. In physics, we would always say it's exactly the data, but what Paulo showed you is that you had a logistic growth, but you have a kind of, there was a region, which is the, physicists call it error bars, right? But it's region of confidence. Then obviously there could happen things inside of this region, of, which is not completely precise, but the data, the theory is at least consistent with your observations. Okay, so that's it's more like that. The validation is different in this case, and then it's not exactly like it's not like physics. Okay, it's theory that will have implications, and then you will have measurements, but the measurements in an ecological context are never precise, and you cannot have the conditions that you would have in a laboratory, which isolates your system from the rest, and then you can study precisely what's happening with your system. It's not possible. The ecology is observational, and except for microbial ecology, it's observational. So you can have some interventions that people call experiments, but it's not exactly the same experiments like the physicists mean. Okay. So okay. Now I remember a further thing that I would like to mention. So, okay, exponential growth. So you can have, in many cases, you can have exponential growth during a certain period of time, and then, okay, something happens. So one thing you have to always pay attention when you build models is that what is the time scale which is implicit in your model? Okay. So here, obviously, with the exponential growth, the time scale would be for a certain time, which is given by the limitations of your observations and so on. And even if I write something that where you could take t as large as you want, actually, that's not a good thing. You have the validity of your models have an implicit time scale, and the models that you build should take into account what are the important effects on that time scale. Okay, so I will show you if everything works well, which is usually not the case with computers. Just a plot. Let me put this. So it worked. Okay. So this is an example of human population. So there the people from demography love to estimate populations in the past, okay, by many methods. So this is the estimated population on Earth between 500 and 2000. So in this case, I don't have a pointer actually. Okay, I will. You can see that there's kind of pretty much an increase, but there are some ripples. Yeah. Okay. So, but if you go for a larger time scale, which is estimation of population between minus 4,000 and 2,000, 6,000 years, that actually almost completely disappeared. So this here looks like exponential, okay? Because we are taking 6,000 years, okay? If you take only from 1900 to 2000, obviously you won't see an exponential anymore. You know that they are not in exponential phase. But if you look at this scale, actually the exponential is okay. And now if you go for very smaller case, so this could say there are enough resources on Earth for exponential growth when you talk about this scale, okay? But now, if you go for much shorter time scale, and I don't have it for the population of the Earth, but for the population of Europe, you can have things like that. That's population, estimated population of Europe between the year 1000 and the year 1700. So it is complicated, at least. Okay? It's not just nice exponential growth. It's not. Okay? So in order to, if you want to do studies about your population on that time scale, it's not enough to say there's enough nutrients, nothing opposes the increase of the population, so no, there's something happening. Do you have a guess what happened here? Hmm? Yeah, the black plague. Okay? So this is clearly a situation where you had human population increasing, and then comes the 14th century, which was a very dramatic century, not only because of plague, it was a famine, it was a horrible century. And in the middle of this century, you have a drop, a real decrease of the population due to the arrival of plague. And then, okay, this first wave goes away, but then you go up there and you see there's another a drop, and then it goes on, okay? And actually, this second this second decrease more to the end of our axis. It is something connected. I mean, it's more or less a joke, okay? But anyhow, this is, if you take it in England, this is 1666, okay, which is called the Annus Mirabilis of Sir Isaac Newton, where he wrote his theory and so on. And he was where? Oh, he was under a tree, people say. But okay, he was not in the city. It went away from the cities. Why? Because there was plague in London at that time. And you see, what kind of model would you say? You have, in order to discuss this kind of thing, you need models that will take into account at least pathogens. Okay? But well, you also know, at that time you couldn't know, but we know that plague is not transmitted directly from a person to a person. Therefore, there has to be what people call a vector, okay, which is a mediator. Okay? But in epidemiological and ecological jargon, a vector is another species. In the case, it's a fleas, and and rats, which are connecting in, the two cases. They are not of direct transmission, indirect transmission. So you would need to somehow put at least the pathogen, but then you would say, okay, maybe we should also put the rats, but then you don't have any data about rats. No idea. What's the population size of rats? No idea. Okay, so difficult, okay? But, okay, so anything that, but the message is take care about timescales. Timescales are important. Okay? So let's now face the problem that in the world we don't see exponential growth. So we will now proceed to something which is what I will explain to you. It's a phenomenological theory or model. But first, let us make an informal discussion. What can stop the population growth? That can stop the growth of a population? What are the mechanisms that you expect that will make the certain population which was growing either goes to a constant value or drops in population size, it decreases? What are the mechanisms that you could imagine? Resource limitation, that's one thing. Space, limitation, and space can be thought as a resource also. Okay, you need diseases can also interaction with other species in this case. Okay, it's a pathogen, it's also a species. Interaction. Environmental change, yeah, also that that happens. Yeah. So what would be the introduction? You have a say, certain community of a species. This is typical of islands, for instance. Okay, then you introduce some species. What will happen? So there can two things can happen. Okay, predation can happen. Okay, and competition for resources. Okay, so there's those interesting things like introduction of cats in islands and so on, and so cats are super predators. Okay, and further in 2 weeks we will see cats and birds and rats, and so there's a famous paper called Cats That Protect Birds, because they regulate the population of rats. So, and which prey on the eggs of the birds. And okay, so the general aspect is I have a focal species, okay, which I will call N, as we have done until now. Okay, it's a certain population level, and then you can have predators, pathogens, consumers of the species, okay? Somehow consume the species, okay? Induce death. They induce death, okay? So this species is a resource for a higher level in the ecological sense, a higher level of the interaction networks. So this is a prey. And now, another thing is there are the resources. So that N has to have resources, and there are many kinds of resources. There are biotic resources, which is what we would say nutrients in the sense of plants or other animals, or that are that the focal species consumed, but can also be abiotic resources like water, sun, spice. These are not biotic, but can also be a resource. Okay? Okay, so now this here will affect mainly the death rate. Okay? Also the birth rate, because it's per capita birth rate, okay? Also the birth rate, but indirectly. Why would a predator affect the birth rate? Hmm? I don't hear it so well.
They kill the adults. So like if there are no adults in the population, they can't reproduce.
Yeah, there could be selective predation for adults. Yeah, that's true.
Yeah, they could kill the adults.
That's true, yeah. But in general, there are also things like fear, for instance. Okay, so the presence of a predator it can induce fear, and then under fear, there's no reproduction, or it's a decrease in reproduction, for instance. But the main effect is about just suppressing individuals. This is the death rate. Okay. Now, resources will and also something. In order to write a theory for this is top-down regulation. Top-down regulation. And I have to write some. I have to have some idea of how many predators I have. So I cannot write this easily only with my focal species. I need another species. This is a species of the predator. Okay, so somehow this has to come has to be taken into account. If you don't know the number of predators, you cannot know exactly what happens. And now, this is bottom-up regulation, and that's what we will discuss today. And so this bottom-up could affect. So let us go back to our first equation: birth minus death times n. Okay. So now you could think that maybe. So these things are not anymore constants, but maybe they depend on the population size, maybe. Right? So, well, resources that are depleted, they can have effects both on B and on D. So B, for instance, if there are less resources, maybe fecundity is affected. Right? But also, if there are less resources, then there might be individuals that do not have enough nutrients to survive, therefore the death rate is also. But now, then you would say, okay, in order to produce a model, I need to model the resources, which is in principle correct. But we won't do this now. We want to do this next week. So what we will do is say a population that is regulated by this kind of mechanism, bottom-up regulation, which is able to increase initially. Okay, so that initially at least B is greater than D. It can grow, but somehow there's a maximum population size that can be attained. And this is something which you can intuitively think that while there are resources, and then there are biotic and abiotic resources, and then these resources can sustain a certain population and not a larger and larger population. At a certain point, you have a maximum population. Okay? So what we will do is write an equation, and in this equation will be a population, a description of what is happening, and in a way that's called phenomenological. So what's phenomenological? So, what's mechanistic? Mechanistic was, for instance, Malthus. Why? Malthus has the birth and death rate. Okay, you can go and examine the at the level of the individuals of your population, and in principle, if you have access to that and so on, there is a birth rate that's defined for the individuals. Okay, it's the distribution. You will take the average and so on, but there is something like a birth rate and a death rate for individuals. Now, what we will do here is just not describe the resources. Therefore, we can't describe the exact mechanism that is acting. Okay, that's important. So we will do something that cannot be calculated at the level from the individual level and scaled up to population. I will suppose, make some hypothesis at the level of the population directly. So that's phenomenological because it's not derivable from a lower level of descriptions. Right? So what we will say is B and D will depend on N. And the idea is that if the population is small, then B, for instance, birth rate and death rate, will not be pretty much affected by the population size. But if the population increases, then there is something which is the competition for the nutrients. And this is called the intraspecific competition. Intraspecific is because we are taking the competition not between two species, but between the individuals of the same species. And so there is this intraspecific competition, and this intraspecific competition somehow should make B decrease when N is large. Okay? So B should be something like B0 minus something which is proportional to N. Okay, I'm making a linear theory again. Okay? There could be many different ways. And then I need a proportionality constant. Okay? So for instance, it's a constant that we will see the meaning at the end. Okay? So you expect therefore that B is not anymore constant. It is now a function of N. And this function of N is like B0 minus A times N. So if the population increases, this has a negative effect on the total birth rate. And if the higher the population is, then there is a decrease of the birth rate due to lack of nutrients. So we are doing this in a phenomenological way because I'm not saying what the nutrients even are. Okay? And, well, if the population size increases, then what you expect is that the dash rate will also increase because there will be this kind of competition. There are not nutrients for everybody. So also the birth rate is depleted, but also the death rate is increased. Then you would say this is something D0 minus something proportional to N times a constant. Okay? So you always have to have a constant in front of this. So this would be my hypothesis. Okay? So are they the only things that I could do? No, I can do many more. So, but I'm taking just a simple function that increases and decreases with N. It's the simple function. It's linear function. Okay. Question and Mike. Mike. Okay, it's already on your.
This hypothesis is related only to bottom-up regulation?
In this case, yeah. This case is.
Even though we're including a death rate change, it's not top-down?
The death rate in this case is increasing due to the fact that maybe they are starving because their nutrients they have more okay, if we are talking about animals in this case, but it could be also other species, okay? So there are no nutrients enough, and there are many ways of competition. We will discuss competition more thoroughly in Thursday, I think. And because you can have competition where some individuals get enough nutrients and the others don't get anything, okay? So, but then you also have competitions where everybody has a decreased level of nutrients, and maybe this affects the time span of the life, and therefore the death rate also increases.
To see if I understood. So as we're talking about resources and arguing about resources hypothesis is bottom up.
Yeah.
Okay, thank you.
Yeah. So this is the usual jargon in population dynamics and ecology. You think about levels, okay? So this is the bottom level, this is my focal level in this case, and this is the top level. Okay? Yeah, more questions?
I just wanted a better explanation of why the birth rate would decrease, because I understand a higher death rate due to competition, lack of resources, and then juvenile death would probably rise up a little more,
Yeah.
because juveniles need more resources to survive. But why would the birth rate per se?
Okay, so you're saying it's pretty much okay if you're talking about the big animals, actually. Okay, but for instance, if you look for insects and so on, the fecundity depends on the level of nutrients. Okay. For instance, for insects, for many insects, the fecundity depends on the level of resources the juvenile had. Okay, so then you have the plants also. I mean, the plants will. I mean, it's much longer time scales than animals, but plants also. I mean, if you have less resources, then you have less reproduction. Okay? Maybe this is not true for I mean large mammals, but in general there can be. Okay, so now let us work out this. Okay, more questions. Today I'm very, very happy that you are asking so much.
My question is about the death rate. Since, according to the formula, then the value of D will usually be negative because of the minus D. So let me see if I understand it properly.
No. Okay.
Okay. A large n size will naturally increase to the number of deaths because of a high number.
Yeah.
That's why it's a plus there.
That's why it's a plus here.
Okay, then I understood.
And that's why it's a minus here.
Okay.
Okay.
The minus
If you are mathematical minded, you could have an objection here, which is correct, but we won't discuss this, which is this could be negative if n is large. And then negative birth rate is just a death rate. There's no birth anymore, and then messed up everything.
Yes,
so actually, what you expect for the birth rate is something that's like this, and then it goes like this. Okay, it cannot be negative. But we will take it as this way. This will complicate our things very much, because then we have to say how this happens and so on. Okay, so that could be an objection from the mathematical point of view, but we won't do this, and we'll always then make some hypothesis that this don't happen. Okay, that's a simplification. Okay, otherwise I have to do much. Okay, now let me write down this. Okay. Now, you have B0 minus AN minus D0 minus Cn. Is it correct what I'm doing here? Yeah, actually. This is multiplied by n. So that's just plugging in this expression into my equation. Yeah. Okay? No, Cn, I have a plus here, and I have a minus here. Now,
Isn't it plus Cn over there?
what did I do? Oh, it's fine, yeah? No, that's not fine. Yeah, it's fine. They have the same sign. They have the same thing. Okay? Now, I middle bit of algebraic manipulation. I will put into evidence B0 minus D0, which is our old R. Okay? And then, if I put this into evidence, I will have 1 minus A plus C divided by B0 minus D0 times n times n. Okay? Notice that this equation is not anymore linear because you have a squared here. Okay? N times n. It's non-linear. And now I will, so at the end, we had here and this, we had 4 parameters. It turns out that the equation can be reduced to have only 2 parameters in the sense that only this combination and this combination are important. Okay? So I will call this as we had R. Okay? So, and I will call this here 1 over k. And with this, we come to the equation that is called the logistic equation. And I will put this n here. This is the logistic. And now we want to see what will happen. What is the prediction of this equation? Okay?
Sorry, how did the k appear?
I can just go here. You see, it's only the combination here that is important. It's not the individual A, C, B, D. Then I can just say that B0 minus D0 divided by I give it a name. Okay? I give a name to this combination.
Or you just assign it.
Hmm?
You just assign it.
Yeah, exactly. Okay, yeah. And you know, this is, again, this k will be what we call a phenomenological parameter because we have already discussed that R could be mechanistic parameter in the sense that it could measure it before just looking at the population dynamics. This k would depend on the knowledge of A and C. But this is difficult to know from individuals. Okay? Okay, so now we have a logistic equation, and you could be interested in knowing what does it mean, logistic. Yeah? So it's a word that has been just invented by the guy that wrote it. The guy is called Verhulst, which is a Belgian mathematician and physicist, and but worked at Paris at the École Polytechnique, which was very important in the 19th century. Okay? And he was actually interested in population dynamics. Okay, he posed more or less this question. Okay, we know Malthus and so on, and this got forgotten completely. Got forgotten. And nobody paid much attention. At the end, it was published in a mathematical journal and so on. Okay? And this was then rediscovered in the beginning of the 20th century by a guy it's very important, although he has the most important, most of the time important guys have an equation with its name. This one doesn't, but it's a guy called Raymond Pearl. And if I'm not mistaken, he was a professor at Johns Hopkins in the US. And he got actually acquainted with that. And because this guy also invited Gauzy, the guy that Paul talked to yesterday. All these guys are interconnected. So who was Gauzy? Gauzy was Ukrainian, actually, so working at that time at the Soviet Union, and had very few contacts, but he could go to visit Raymond Pearl, and actually this made also, Raymond Pearl was also already interested in population regulation, and then, well, he went on to try to test the predictions of the logistic equations, which we will now work out. Okay, so with flies, with Drosophilus, and so on. Right? This is a nice story. We can look in the. There's a book. I can bring the book tomorrow about the history of population dynamics. Okay, so now comes the. Now comes the mathematical part. So you look at this and say, okay, this is a nonlinear equation. So it is a fact that most nonlinear equations cannot be solved in terms of of known functions. Yeah? Most of them. One exception is this one. This we have a solution in simple form, which is nice. Okay? So now, I know that people that have not had training in the differential equations probably won't understand how to obtain the equation. So, okay, you just get 5 minutes, and we'll talk to people that know differential equation. It's very easy to solve this. You just have to take this. dn over n 1 minus n over k equal to r dt. Integral, this one is easy, and this one can also be solved. It is a logarithm. Okay, so you can go on table of integrals, and this is there. It's a function. Okay, and then you get something here, and you got t here. Then you work out the algebra to obtain n in terms of t, not t in terms of n. Okay, you can work out this. Okay. So if somebody wants an afternoon, I can just show the derivation. But this is particular because of you have n square here, and then there are in the mathematical jargon you know the primitive, and once you know the primitive, this will be a function of n, and this is just linear in t, and then you invert the thing. And you get, instead of t in terms of n in terms of t. So, okay. So if you didn't understand, I have a proposition for you. Believe in me. I will give you the solution, okay, as a gift. Okay, I give you the solution. Okay? So, for instance, we have this mysterious k here, okay? For instance, this mysterious k, okay? It will get a name even, okay? And which makes it a little bit less mysterious. 1 plus k minus n0 divided by 0 times exponential of minus r of t. So, you like it or not, it's again has the elements that we had before. There has to be an initial condition, which is n0. Okay? Well, and You have again an exponential, but it's a negative exponential here because it's 1 over a negative exponential. It's like being a positive. Yeah.
Sorry, just to make sure I understood it, because I don't know a lot about math. This first one, you obtained it by using integral on both sides of that logistic equation we found.
Yeah, I made a small manipulation, which is usually taken to take this as a fraction, actually.
Yes,
yeah. Then you have dn divided by something which has only n. Therefore, you can do the integral.
Yes, yes.
And here you have dt times r, which is t times r.
Yes, yes, I understand. I believe you, don't worry.
Yeah.
I just want to make sure that one came from the other.
Yeah, exactly.
And
this comes from there.
And from this integral, you obtained this new one using the
n0. Here you have a function of n. And you have a function of n, let's say just the function of n, okay? Will be times rt, okay?
Yes, yes.
So then you say, okay, I can now work out this and find the inverse function, actually, meaning that if I can write t as a function of n, I can also write n as a function of t, okay? Because of correspondence between t and n. So it turns out that mathematically it's easier to come out t as a function of n, but you can find the inverse, and then you have n as a function of t.
Yes,
and then I'm asking you to believe it, that all after that you get this.
Using both of these equations, the one down here and the one
down
up there.
Here, and doing all the algebra.
Okay.
Okay.
I believe
so
you.
My experience is that always when I do this explicitly, people get lost completely. If either you had differential equations in your life, and then it's trivial, either you didn't, and people get completely lost. Therefore, that's why I'm not doing it explicitly, because people don't remember how to make an integral and so on. Okay. So, okay, now, complicated expression, what do? We plot. In order to plot, I need to have numbers, yeah? Because without numbers, I can have plots. Then I have to think about, okay, I have to put r and k and then 0 in my, I have to give them some numbers, okay? Well, if you do this, and usually you would do this on a computer, you will get the following general picture. Here's time, here's n. And here's the value k. And if I start with n0 here, let's put more here, you will start by growing exponentially and approach the value k over time. So the mathematical jargon for this is that the function n approaches a constant asymptotically. Okay? If I start with n bigger than k, then this goes here, and it will just decrease. And at the end of the day, asymptotically, the population tends to a constant value. So prediction of the logistic model is, with any initial condition I start, I will, over time, approach the value k and stay at a constant level. That's the prediction of the logistic model, which has the ingredients that we have discussed. Okay? So this says, if I modify Malthus law, I will have an initial phase which just looks like an exponential, and then the exponential would go here. Now it deviates here and goes to this value. At the end of the day, you have a certain value, which is this k. Okay? So, very nice. And now, let's talk about k. Okay? So, when you look at this, I told you we cannot calculate k from first principles. It's just a number. Okay? It's just a constant parameter here, which is modeling what? Whole relation of your focal species, which is n, with nutrients and environment and everything. So it's just a model saying that nutrients, environment, space, everything will have the effect of creating a maximum population size that can be sustained by this environment with these nutrients. Okay? And this population size is k. That's the maximum population size that can be sustained in a certain situation. So, important. You can ask, we thought about R for E. coli, or we thought about some imaginary elephants or whatever for human beings or the cows or whatever. And we related R to the doubling time of the species and so on. And so you could go there and say, the doubling time of E. coli is this. Right? Now you say, what's the current, okay, this has a name, I didn't say the name. This K is called carrying capacity. Which in Portuguese is usually translated by capacidade de suporte, which most people use. But this is actually an Anglicism. Support in this case it comes from supporting something, which is not exactly the meaning of support, suportar in Portuguese. So there's a better translation which is used in the translation of this book of Gotelli, which is capacidade de carga. But this is, I mean, just a small comment about people will use capacidade de support most of the time. Okay.
Let me ask, we are still considering only bottom-up regulation?
Only.
Only. Okay. And I have another question about the value of K, the carrying capacity, because when you assigned the K value to a part of the equation, there were the A and C, which were two constants you assigned to N. Since K is the carrying capacity, can I conclude that A and C are both constants related to the amount of resources in the environment?
They model the effect of the competition for resources. You have to the A and C are, there's a term, it was written somewhere, you had A times N, okay? We had B minus AN, for instance, okay? And corresponding for that rate. So if N is very small, okay, then this is not important, okay? I mean, if this is 10 to minus 5 times this guy, you just neglect. Okay? So this is important if the population is large. Okay? If the population increases, then there is competition for the resources. Okay? The competition for resources, and we will discuss this when we talk about competition between species, but it's also true for intraspecific competition. Competition for resources is only important if the resources are finite and has to be competition. If let's say we compute for food here in this class, and I bring you 1,000 sandwiches, 1,000 hamburgers, nobody has any need to compete. You can eat and up to satiation and you're. Now I bring only 10. They will fight for the hamburgers. Okay, so that's a caricature. I mean, it's just a joke. But So competition is important when the population sizes are at a certain level where the resources start to become the mechanism that regulates the population. And this is important if the resources are, if the population is such that it consumes the resources and depletes the resources to an extent that this effect on birth and death rate will be important. So if n is very small here, then you can just neglect it, okay? And yeah, okay. So what was I going to say now? Okay, about the carrying capacity. So this is a combination of these things, but as you could not measure n, a, nor c, whatever, you just stay with the combination, which is k, okay? And so there's no sense of saying the carrying capacity of a certain species. What's the carrying capacity for, say, some plants in a certain region? This is nonsense. You have to say the carrying capacity is a relation between the nutrients that you have there and the environmental conditions and the species. Therefore, it's not, I can say the carrying capacity for, say, lions. Well, it depends on the nutrients. It depends. If a lion is living in a place where there's no nutrients, then carrying capacity is small. If there are lots of nutrients, a lot of zebras or whatever, then the carrying capacity is larger. It is not intrinsic to a species. It is a relation between a certain species, the species that you are studying, focal species, and the environment and the nutrients. Okay? And that's why I'm saying that is a phenomenological thing. Okay? Because you cannot measure K from individual things. Okay? We will see that we'll have progress on that when we discuss something that's called consumer resource dynamics, which is a way of not having the carrying capacity or deriving carrying capacity from the nutrients. It's just very elegant. Next week we will see. So, okay. So the message of a logistic equation is we have an initial phase of a strong increase, and then we go to a constant value. Or if we are above the carrying capacity, we just go down. Okay? We could actually see a lot of things just from the equations, okay? Like that. So let us make approximations. So approximation says that this here, okay. Now suppose that the population size is, at least at a certain point of time, much smaller than the carrying capacity. Okay? So if this is much smaller than 1, this is 1, we can just neglect this and have dn dt equal to Rn, which is multiple exponential growth. So if the population size is much smaller than k, you have exponential growth, which is what I showed here. Okay? I mean, here I just said it was exponential, or approximately exponential, but didn't show you. Now, it comes out directly from the equations that that you have this. Okay? So you have an exponential phase, but this equation is such that if n increases, this inequality will not be any more true. It will be of the same order of magnitude at 1, maybe 0.8, 0.9. And then that's not anymore true, and then you cannot neglect it anymore. So the dynamical evolution of the population size can be such that if you start with a small population, and now we can speak about small populations. Small populations in this framework is a population whose size is much smaller than the carrying capacity. in this environment, right? Then this is the definition of small population, okay? And small populations will grow exponentially, but the equation itself is such that when this grows, this is not anymore true, therefore it's not anymore malthus, it has to be taken into account the full equation. And the full equation has this solution, which is plotted there, okay? We can also see that another thing that can be derived easily here is, say I have a population which is exactly equal to K, carrying capacity. If N is equal to K, N over K is 1, 1 minus 1 is 0, and dN dt is 0. Constant population. So these are both ends of the argument. Population small, exponential growth. Population at the size of K, constant value. Therefore, the dynamics is growth, saturation, going to a constant value. That's the logistic equation. That's the model for. And then you could say, okay, maybe it's not equal to K. Yeah? It's a little bit K minus, not K, it's a little bit below K. Yeah? Well, then if you do the math, then you see that this will give you that the derivative is also very small. And if the derivative is very small, means that the increase is also slow. Okay? So that's it. Now, so what's the importance of the logistic equation? So the importance of the logistic equation is that it allows us to introduce the idea. First, it is a remedy. It is much better than malthus, because malthus, but all populations go infinity. Now, you say constant population. We see constant populations, and we also see increasing populations that saturate. So that's more realistic. We should be happy with that. But obviously, this is not everything that happens in the world. And we will discuss a lot populations that oscillate in time. Increase, decrease, increase, decrease, and this is not described by that. Oscillations in time will be connected to top-down regulation, actually. Okay. Yeah.
It's true. I was thinking about annual, I don't know if that's how it's called in English, but like annual plants. Herbáceas anuais. Herbáceas anuais.
Bases anuais. O que é base?
Herbáceas. Herbáceas anuais, aquelas que morrem. E
herbáceas.
And is that considered a fluctuation on? Yeah. Okay.
So here we went from Malthus' equation saying that everything increases forever, and now we come to the logistic equation that says that after some increase, then everything will be constant. And then you look out and they say, no, it's not true. Okay, but I mean, it's better than Malthus, because their population is constant. Okay, over a certain time span. It's always a certain time scale. Okay, and things that we are, for instance, talking about ecological time scales, or we are not talking about evolution, for instance, it would be larger things. And now you could have also that the fluctuation of the environment are time dependent. For instance, you have the seasons, or you have day and night, or you just have some random weather effects from rainfall and so on, and all of this will induce fluctuations, and the populations will not stay constant. Maybe after the perturbation it goes back to what it was before. So there are many perturbations that can induce this kind of fluctuation. So for instance, seasonality. Okay, seasonality is something that can be modeled if you want, saying that the carrying capacity, say in spring and summer, has a certain value, but in autumn and winter it has a much smaller value. Okay, then you would have that the carrying capacity itself may depend on time. Okay, this is clear for plants. Okay, most of the time, the carrying capacity of a certain landscape or it can depend on if it's summer or winter. Okay, then that's normal. Okay, and then you would say that the carrying capacity could depend on time, which is some way to model the effects of seasons. Now, what we will see that, so I don't want to induce you to error to think that all fluctuations or population cycles, okay, come from the environment. That's not true. Okay? We will see that top-down regulation can induce intrinsic cycles in populations, which is very interesting, right? That it intrinsically oscillate, not due to something external. Okay? But this has to do with top-down regulation, which we will discuss also in the next few classes. So, okay, so and one of the things about the logistic equation, it's nice that we could introduce this carrying capacity, which is useful in many situations, because, as I told you, it is at the same time, it has many glories, but it has also many miseries. The glory is that it is an easy way to model a complex set of interactions that regulate the population from bottom up. And all the regulation turns out to be encompassed by a single constant and parameter. This is not, obviously the misery is, it's not calculated from anything. It's just, how do I know the carrying capacity in a certain situation? So that's less discussion for this class. It's more epistemological. So how do I know the carrying capacity? Okay. So there are, I told you, I could go there and measure things. Okay. But carrying capacity, it's phenomenological. It's a whole set of relations, and I can't measure K. Therefore, this equation is, in a strict way, non-predictive, because K cannot be given beforehand. How do you know K? You just perform an experiment, and then you get the constant population, say, okay, the constant population is 1,000 individuals. Okay, then it's K. Okay? But this was not predicted by anything. You just get it after you ran the experiment. Okay? Then you can say, okay, K was 1,000. Right? But you know, you would want this to be a model that could be proven wrong. I mean, proven wrong, not exactly. But the model could make predictions, and you say my model is okay if the predictions are confirmed. But this model cannot make any prediction because you cannot never know K. You just K, then you run the experiment and you get K. But this is tautological, obviously, because you had made no prediction. What you can see is say it's compatible because it's a constant population. It's compatible. Okay, that's okay. But there's no actual prediction. Okay, it's not like Malthus. Malthus had a prediction. We know that it's not realistic, but it has a prediction. Here, the prediction is the pattern. Populations increase and go to constant size. Now you want to be more than pattern. You say, I want to know, I start now with a certain population, a certain system, a certain environment, a certain number of resources, and I want to know what will be the final population when it gets to a constant value. No way. Problem. No way. Because you don't know K. So you could then say, okay, now this is the case that we should try to write models whose outcome is K. So maybe I can know all the nutrients and all the circumstances that at the end of the day produce my K. Would be modeling the carrying capacity. And that's a game that's played in town. Okay? That's still something that makes sense. Okay? That's called a mechanistic intercompetition theory. Okay? So it's not phenomenological. The point about phenomenological theories is this. We cannot get K and say I have K, and now I predict that population will be certain size after certain amount of time. So you only have the K after you run the experiment. Therefore, you did not predict the outcome of the experiment. The outcome of the experiment just says that it's compatible with a K with certain value. Okay? So this is different from mechanistic theories. For instance, predator-prey dynamics is usually a mechanistic theory where you have attack rates. And the attack rates can be calculated before looking at the population. You can look at an individual attack rates, and then this will make sense. But for competition in this way, it's a little bit, wait, you raised your hand? Yeah, yeah, where's the mic? Okay, so you have to stop.
If we replicate the experiments, if we replicate the experiment for many times, we can have the values of K, the variates values of K. And in this case, we can have the data to build model to make prediction.
Yeah, I mean, okay, you would say, I mean, you could do many experiments and then say that you somehow found a way for the input is the environmental variables, and the output is K, and I could do machine learning with this if you want, or just some statistical correlation or regression, and say, okay, given the environment, I know K, and then I make predictions. Okay, but this comes at the expenses of somehow having a model for K. So it can be a model in the sense of mechanistic model, or it could also be just some knowledge that is empirical, which is actually what is machine learning in this case. It's empirical. You know, you do it so many times and you get these correlations and you say, okay, this will be probably valid. And if I put some other environment, and I can make a prediction. In this case, yes. But this is always, somehow you have to know K in order to make predictions. So, and the point about logistics is not so much make predictions, because it's a single species. It's not interacting with the, I mean, it's interacting with the environment, but it is a model that it describes some situations actually, but it is more conceptual model that says that, okay, we can have a better theory than Malthus, and then you go to constant values. Now, if you don't see constant values, you ask the question, why it's not constant anymore? What's the mechanism that is making it not constant? And that's the way you build the theory, okay?
Well, in the beginning, you said that this differential equation is not linear. What is the consequence of that?
The consequences of that is, in practice, you want, I mean, so here you have, because you have n times 1 and n times n is n squared is not linear, okay? It has to be power 1 to be linear. And so most linear equations you can solve in terms of known function, most of them. By chance, this one is also possible to solve by in terms of known functions, which we wrote down, it was somewhere, the expression, okay? So actually you can transform these variables and transform this equation to a linear equation. That's the reason it works out for this case. And but say you have put the n squared here. Then when you manipulate the integrals and so on, there's a point I have to do an integral of 1 over n minus n in this case, cubic, say. Eh? And then you don't know this integral. This integral is not, does not have a primitive. It does not have a function that we can express in closed form in terms of known function. And it doesn't. It exists, but you cannot write it down. And this is then the obstacle of obtaining analytical expressions. And then you have to resort to computer simulations, like Renato will show you. That will be part of the Renato lectures. It's how to solve equations that you cannot do the analytical manipulations. But we can do more than this. And I will discuss briefly this in the next class, which is called the qualitative dynamics, qualitative analysis of differential equations. So qualitative analysis will be something like what? So I don't care to have exact solutions. I don't care. I just want to know what this has been important here is it increases and then goes to a constant value. So this is qualitative. It's not saying exactly the same. Okay, but knowing the qualitative dynamics is already a lot. And when you don't have the expressions, it's a way to really understand the system is through qualitative dynamics. And we will do extensively when we talk about competition and we talk predation, everything, qualitative dynamics. Okay? So, Flavia's here already. Okay, so that's all for today. So see you tomorrow.